So, this will be the last lecture on nucleation kinetics in the solid state. So far, we have really looked at liquid to solid transformation and nucleation in liquid to solid systems. Now, what happens to the nucleation rate in the case of solid to solid transformation? So, here we are going to look at nucleation kinetics in the solid state. What things change? Mostly it remains quite similar to what we have done in liquid to solid, but there is going to be some additional terms that would come in. For example, in any phase transformation, there is a volume change. Now, this volume change gets accommodated in the case of liquid to solid. So, if a solid, let us say, expands, the liquid around it accommodates it. However, in the solid to solid transformation, if the nucleus that forms expands, then it will tend to deform the surrounding parent phase. As a result, there would be a strain energy that would be introduced in the system. This strain energy, as has already been discussed in earlier lectures, would be associated with a positive change in free energy delta Gs, where S is standing for strain. And as a result, what happens to the critical size of the nucleus in this case? Well, the strain energy term would also get into the relationship, and let us say we have a transformation of alpha going to beta. So, our beta nucleus is forming from alpha and there is a volume change. As a result, a strain energy term delta Gs comes in. Then the critical size in this case would be 2 gamma alpha beta upon delta GV minus delta Gs. So, here it is clear that the critical size when a strain energy term comes in would be bigger, larger than in the case where the strain energy is negligible or 0. And what happens to delta G star? We are here just looking at homogeneous case. So, let me also write it as homogeneous. Well, this becomes 16 pi by 3 gamma alpha beta cube upon delta GV minus delta Gs cube. So, the free energy associated with the critical size nucleus also goes up, so the energy barrier is higher. So, with the presence of strain energy, one would expect nucleation to become little bit more difficult or would require further undercooling because of the transformation which takes place with the change in volume. Of course, strain energy is produced from various factors. One of them is just volume change, the kind of interface that is formed, whether it is a coherent interface or an incoherent interface, that will also play a role in the strain energy. However, I will not go into the details because in earlier lectures this has been dealt with in quite some detail. If I look at the nucleation rate equation, I is equal to I naught exponential minus delta G star upon kT times exponential minus delta GD upon KT. So, what are the terms that are changing in this in the case of the solid transformation? So, delta G star would be somewhat different. So, if it is larger, then the nucleation rate will go down for the same amount of undercooling. In the last lecture, we had also looked at I naught, but I naught in the case of homogeneous nucleation would be of similar order that we have already got, to the order of 10 to the power 40 or so. But in the solid state, the heterogeneous nucleation case, the situation would be similar in the sense that the free energy for the heterogeneous nucleation would be related to the homogeneous free energy multiplied by whatever shape factor that is there. So, for example, in a polycrystalline structure, if the beta phase is forming on the grain boundary, it might be forming in a lens shape, which also has been dealt with in an earlier lecture, which would have a somewhat different value of the shape factor than what has been considered earlier in the last lecture, slightly different value by a factor of 2. So, then what happens to the nucleation rate from all of this? Well, the strain energy of course changes this. If it is a heterogeneous nucleation, that changes that. Again delta G star, invariably in the solid state, heterogeneous nucleation is the preferred route for formation of nuclei. In large number of systems, for example, in austenite to ferrite transformation in steels, the pro-eutectoid ferrite tends to form on the grain boundaries of the austenite grains. And so, what happens to the nucleation rate? So, delta G star has changed, as we have already seen. Now, I want to explore I naught. What happens to the factor I naught in the nucleation rate expression? Well, in the homogeneous case, I naught we have been taken as of the order of 10 to the power 42 for metals, 10 to the power 42 per meter cube per second. Now, I want to explore how I0 will change in the heterogeneous case in the solid to solid transformation. Remember that what is I0 from a previous earlier lecture? I0 is N0 Ns nu times P. N0 is the number of atoms per meter cube. These are the number of atoms surrounding the critical nucleus per unit area per meter square, let us say. This is lattice vibration frequency, which is of the order of 10 to the power 13 per second, and this is probability of a successful jump from an atom in the parent phase to the and the atom joins the nucleus. So, let me this. Now, in all these terms, N0, the number of atoms per meter cube, in fact, this number of atoms per meter cube is taken in the homogeneous case as the number of sites for nucleation per meter cube. This is for homogeneous. Now, the number of sites in the heterogeneous case, how are they going to change? And let me consider two choices, or rather let me consider two sites of heterogeneous nucleation. Let me consider one as grain boundaries as sites for nucleation. So, what suppose I have a polycrystalline microstructure and I have these polycrystalline grains in the system. This is alpha and I am considering, let us say, alpha to beta transformation. So, one way this beta phase can form or the beta nucleus can form is this nucleus at grain boundaries. So, these are the lens shaped nucleus, that is one shape that is possible for which the analysis has already been done. Now, the thing is, for beta to form I have certain density of grain boundaries, and that density of grain boundaries is going to determine what would be the number of sites at which beta can nucleate. So, the density of grain boundaries is going to govern what is going to be the site of nucleation. So, let us try to estimate that. How do we estimate that? Well, what I need to know? I need to know what is the surface area per unit volume of grain boundaries. So, I need to know this. I need to know what is the thickness or width of grain boundaries. So that I can calculate what is the volume of grain boundaries or the volume fraction of grain boundaries in the material. Once I know this, then I would be able to estimate what kind of a order of magnitude estimate for the density of nucleation sites. So, let us consider, let us take in the case of any metal that grain size is of the order of 5 micrometers. Obviously, if I have small grain size, I will have lot of grain boundaries, large density of grain boundaries, larger number of sites of nucleation. If I have coarse grains, I will have less density of grain boundaries and hence less number of sites of nucleation. So, grain size, let us assume, is order of 5 micrometers. Then the surface area per unit volume of grain boundaries, what is the surface area of these boundaries is, and we are only doing an order of magnitude estimate, is of the order of 1 upon 5, just the inverse of the grain size. And let me write the units as micrometers upon micrometer cube, which is equal to 0.2 micrometer square upon micrometer cube. What is the thickness or the width of grain boundaries? Well, typically one can assume a width from 1 to 8 atom thick. Let us, for our purposes, let us assume a grain boundary which is only 1 atom thick. So, for example, a metal like copper, the diameter is of the order of 0.3 nanometers, which means the thickness of the grain boundary, I can assume it to be 0.3 nanometers. So, what is the now the volume fraction of grain boundaries in a material like copper? which has a grain size of 5 micrometers. Well, that would be simply surface area per unit volume multiplied by the thickness or the width of the boundary. So, that is 0.2 micrometer square per micrometer cube multiplied by 0.3, this is in nanometers, let me convert this to micrometers. This turns out to be 0.06 into 10 to power minus 3, which is equal to 6 into 10 to power minus 5. That is the fraction of boundaries present in the material. So, what is the number of nucleation sites then? On the grain boundary? Well, that would be, let us just take 10 to the power minus 5 as an order of magnitude estimate for the fraction in this case. So, it is 10 to the power minus 5 multiplied by how many atoms are going to be there on the boundary, because each atom then is the potential site. Well, that number is N0, which is of the order of 10 to the power 29 per meter cube. So, all I have to do is multiply this with 10 to the power 29 and I will get an order of magnitude estimate of the nucleation sites on grain boundary as 10 to the power 24 per meter cube. So, therefore, I0 directly, where I0 is this, will become several orders of magnitude smaller as compared to in the case of homogeneous nucleation. One can also see that if I, let us say, take a very coarse grain like 50 microns, so I increase the grain size one order of, the density of nucleation sites will reduce magnitude by this simple calculation. Similarly, let me pick up one more site where in solids nucleation takes place and which is on dislocations. So, let us try to see what kind of an estimate one would get where heterogeneous preferred nucleation would be on dislocations. So, dislocation sites of nucleation Now, in this case, let us try again order of magnitude estimate. In annealed metals, the density of dislocations rho is of the order of 10 to the power 10 meters per meter cube. So, dislocation density is measured as the total length of dislocations in a unit volume of material. So, in this case 10 to the power 10 meters per meter cube. If I looked at heavily cold worked metals, in heavily cold worked metals, the density can go up to as high as 10 to the power 16 meters per meter cube, sorry, this is meter cube. Now, on these dislocations, what would be the density of sites? This could be calculated by considering that dislocations has a certain core width. So, we also have to have an estimate of the dislocation core width or the width of the dislocation. You can imagine that this core is in the shape of a cylinder. So, the dislocation core width radius r is of the order of 1 Burgess vector to about 4 times the Burgess vector. Now, in a metal like copper, we can put Burgess vector to be of the order of 0.3 nanometers. And let us just assume for purposes of order of magnitude estimation that the core width is just b, which means 0.3 nanometers. Then let us do an estimation for, let me write down here, annealed metal, cold worked metal, dislocation. Let's try to calculate dislocation volume fraction. So, fraction of the material occupied by the dislocation core, this is equal to 4 pi r square times the density, which turns out to be 10 to power minus 9, while in the case of cold work this would be the fraction of the material occupied by the dislocations is 10 to power minus 3. Therefore, the number of or the site density, number of nucleation sites on the dislocations in the case of annealed metal then is 10 to power minus 9 multiplied by density of dislocations in the annealed metal, which I am taking it as the order of 10 to power 10. No, just a second. What did I do? No, sorry. We have already taken this density. This is the fraction 10 to power 9 minus 9 multiplied by N0 10 to power 29 atoms per meter cube. So, this gives me an order of magnitude estimate of 10 to power 20 sites per meter cube. What happens in the case of cold worked metals? We have much higher density of dislocations. This number turns out to be 10 to power 26 per meter cube. So, what we have seen is that in annealed metals you can have, if I look at it from the homogeneous case, the number of sites for nucleation can drop down by as much as 10 to power 20, and in fact it can even go down even lower if we specially make materials which have very low density of dislocations. Then it could even go down to the order of 10 to power 12 to 10 to power 13 per meter cube. So, if I then look at what is the value of my I0, well, in this case, for example, grain boundaries, I0 would be of the order of 10 to power 35. So, in the case of grain boundaries, value of I0 then would turn out to be of the order of 10 to power 35 per meter cube. Here in the case of dislocations, this will come down to I0 would come out to be the order of 10 to power 31 and could go down to as low as I0 to be the order of 10 to power 25 per meter cube per second. So, we have seen in this lecture how the nucleation sites can change depending on what kind of heterogeneous site is available. With this, we conclude our discussion on nucleation and nucleation rate. In the next lecture, we will be talking about once a stable nucleus is formed, what would be the rate at which it will grow. So, we will look at growth kinetics. Thank you.